Hello, everyone. I'm Elia. I'll be speaking about visualizing mobility data. So the previous talk was about like preparing, collecting data, but we need to be able to analyze it and understand it. We need good visualization tools as well. So I am a software engineer. I've been working mostly on geospatial data visualization. And yeah, I've participated in many projects working with mobility data, representing it in various ways, and my PhD was focused on that topic as well. Also, I was working for a company called Teralytics, where we visualized mobility in cities, how people move in cities, for different transportation providers to help them understand the demand and improve their services. And so we built this dashboard which allowed people to look at mobility data in cities. And the company I worked for was generous enough to allow us to open source this flow mapping layer as an open source library, which we did. So there is a Flowmap.gl library, which is a deck.gl layer, custom deck.gl layer implementation. If you are familiar with deck.gl, which is a framework for efficient geo data visualization. So this you can use, but then I realized that like not everybody is a programmer. It was a couple of years ago. Now everybody is, of course. So so I developed a tool which people can use without having to know how to program in JavaScript, which is like you just throw some data, OD data, must be in a particular format, to a Google Sheet, Google Spreadsheet. Then you just like paste the URL to this tool, and it will magically visualize it as an interactive map. And people started using it and publishing stuff. That was pretty cool. Then some people started to contributing back, like there is a, for instance, R integration developed by Igor Kotov, somebody from the community. So yeah, briefly, what is a flow map? Who's familiar with the concept flow map? Oh, not that many people. Okay, so it's about visualizing numbers of movements of people or whatever, it can be goods, whatever entities, between pairs of geographic locations. You're not very interested in the exact route the people take. It's more about how many people or entities moved from A to B. And then you can have additional attributes like time or mode of transport, whatever. And so a flow map is a way to represent that, and often thickness of the arrows is used to represent the amount of people moving, or the color. Or sometimes you see this animated particle animations, like the number of particles will be representing the number of people moving. And the direction is important as well. So arrow is a like naturally understood representation of that. And the kind of data which is can be represented that way is often called origin destination data, OD data. So you have basically a table, you have origin, destination, and count. You can have additional columns for attributes like time or mode of transport. So in developing this tool, I put a lot of effort into making the visual representation very readable, very understandable. So in Flowmap.gl, like there is a double encoding for the amount of people moving, number of people moving. It's the thickness and the color. There is also the sorting of the arrows so that the most important ones are at the top. Arrows have outlines so that when you put a lot of them, they overlap. You don't have they're still recognizable as individual arrows. Then there is fading, which is like you can configure. Basically, it's the amount of downplaying the less important flows you can adjust. They get darker. And this plays well with blending, which is used in Flowmap.gl. So basically, it's a way to make sure that the underlying base map is still readable, even when you have like thousands of arrows overlapping. And it's not, it wouldn't work with just opacity, because with opacity, when you have overlapping arrows, they would still, like the color would still add up, so you wouldn't be able to read the underlying map. But with the blending, or you can just use a CSS blending, because the arrows are rendered in the separate WebGL context. This is a technicality. But never mind, you can make it so that despite thousands of overlapping arrows, you can still read the underlying base map. Then, the location totals are represented as circle sizes. It's a bit more complex than that, but I won't go into the detail. There is an alternative way of representing the directionality of the arrows. You can use this fancy animation. Sometimes it's actually more readable, but often it's just like more appealing. But still, like with all these techniques, often you have too many flows, which are kind of producing a noisy picture, and reducing the performance is not that great when you have to render all of them. But many of them are actually noise. Like here, you see there are flows which start and end outside of the viewport. What's the point of rendering them? They only obscure the picture. So what Flowmap.gl is doing is actually an adaptive filtering. We filter the flows so that only those which are within either start or end within the viewport are rendered. Also, we don't show more than like a certain number of flows. 5K is a good number, but you can adjust that. So when you like zoom in, you see the detail for this particular region. We also adjust the scales, right? So when you zoom in, you see the flows which are the largest for this particular viewport will pop up. So this way you can explore the regions in more detail when you zoom in. And it improves performance. Still, you often can get some messy data sets, like this one, which is bus travels in Sao Paulo. Here, like the length of the arrows is relatively long compared to in relation to the distribution of the locations. So you get lots of overplotting, right? And it's not very readable. Or here, the opposite extreme. You have migration in Australia, where like most people migrate close by, right? Not across the whole country. So here you basically don't see the flows at all because they're too short. So how can we address that? Maybe we can like create a useful summary which would work at any zoom level and for like independently of what the exact distribution of the locations and flows are. So for that, Flowmap.gl is doing hierarchical clustering. So who is familiar with hierarchical clustering? Some people. Okay, so I'll explain. Basically, we have the locations. We calculate the total flows for the locations, the total outgoing, incoming, or like it can be different metrics, but how important basically the locations are. And we start with the largest so that when we group them together, the largest have the most, like basically define where the cluster will be located, right? So we don't move the Brussels to some smaller location. Then we we have some, for every viewport we have zoom level, we have a certain radius within which we group together the locations which are close by to the locations we start with, right? So we group them together, we get the clusters, we move them into the center of masses weighted by the total flows. And we get like the clustered locations at this level. Now we have to recalculate the flows so that we basically aggregate all the flows between the constituents of the clusters, and we get the new flows at this zoom level. So this way, we get aggregated summary for this particular zoom level. And why it's called hierarchical is that we can repeat this process and go up and build a hierarchy of clusters for a number of zoom levels we are interested in. So with this approach, from these messy data sets, we get something like this, which is much more readable, but when we just look only at this zoom level, we lose the details, right? The good thing is that this is fast enough so that we can do it interactively. We zoom in and out, and clusters will expand and collapse depending on the zoom level. So this is a public transport in Brisbane, and you can see you can zoom in and see more details about the particular region, how people move there. This is through traffic. So with this approach, this is also through traffic. It means it's not like origin destination, it's how many people move within each segment, which can also be kind of converted into OD. This is public transport in Zurich, and here there is also a temporal dimension. You can and you can filter by the tram line or over time. So, by the way, this app is not open source, but much of the technology behind it is, and I'm going to open source parts of it as a part of a new project I will mention. But this one is using DuckDB. Who's familiar with DuckDB? A few people. Okay, so this is a pretty cool database which has some advantages for this kind of use cases. First, it's made for analytics. It's using a columnar data representation, which makes queries aggregation, for instance, are pretty efficient. It's also embeddable and really anywhere. So this example I showed you before, DuckDB was running in the browser directly, so there's no backend serving these queries. And every time I zoomed in and out or moved the viewport, there were like dozens of SQL queries preparing the data for this particular viewport. And DuckDB, since it can run in the browser via WebAssembly, it can do that, and it requires very low infra setup. So basically, you just need to download the data from an S3, like a Parquet file, add it to the DuckDB running in the browser, and you are good to go. You can run queries directly in the browser. So yeah, in this app, like when you load the data set, it will prepare, it's too small, I know, but don't worry. It prepare like pre-aggregated tables, which will make it easier for to run later queries for a particular viewport to get the data it needs. So like for different zoom levels, for instance, right, there is a mapping between original locations and clusters on each zoom level, so that it can quickly do the mapping and prepare the data. So this demo, if you want to try it out, you can quickly scan. I won't be showing it for the sake of time. Yeah, now I'm working on this new open source project. It's called sqlrooms, and it's basically a framework which helps you to build data analytics apps, and it's kind of backed by DuckDB, and it's very modular. Like there are different kind of modules you can functionality you can you decide which functionality you want to add into your application. It has like basic dataset browser, database browser. You can see the tables you have. You can have an AI assistant which will generate queries for you, SQL queries which can still run in the browser without sending data to any LLM providers. Many things. And I'm also, it's been used by several companies specifically for data intense and data visualization applications. And I'm working now on, there will be an example showing a Flowmap, which serves the data directly from DuckDB in the browser. And as part of this work, I wanted to have a demo for this conference, but I haven't managed. Life got intense. Sorry about that, but it's like work in progress. I'm explaining what I'm working on. So for even larger datasets, DuckDB is already pretty powerful. You can have like millions of rows in your OD, in your flows table, and it will be good enough. But what if you have like many attributes or small temporal buckets? The number of rows in your table, in a flows table, will multiply very quickly, and at some point it will be too large to load the entire thing into the browser, and you want to avoid that. So, but what you can do, you can prepare your data set in a way so that you can only fetch parts which you currently need for the current viewport, right? And DuckDB supports HTTP range queries. So basically, if you have a Parquet file somewhere in S3, and it has a column by which you can filter, you can say I want like this range for values of this column, and if the rows are sorted in the right way, then it will only need to read those parts of the table which satisfy your query condition, right? So if you can do it this way, then it will be fetching data on demand, like, as you change your viewport, without having to load the entire table. And so to do this, who is familiar with space filling curves? Just a few people. Okay. So this is a mathematical concept, but it's actually easy to explain. The purpose is to compress 2 dimensions into a single dimension. So you have like 2 columns, x and y, right? Or latitude, longitude. Better use x and y projected already. And then you wanna. These are 2 numbers. You can save them separately. But our purpose is like to have a column by which we can sort, so that then it will be easy to query, so that the things which are close to each other, are also close in this table, close to each other, so that we can. We need to fetch fewer chunks, right? And so this is a way to do that. Basically, you draw a curve which would fill the entire plane, right? 2D plane. And then, like at every junction, you put a number, 1, 2, 3, 4, and so on. And this number is the index, right? Which you can then put in your column. And this way, you can reduce 2 dimensions, x and y, into a single index, right? And this will be the number you want to sort it by, so that you then need to read fewer chunks from the table if you sort by this number. And DuckDB has a function, st-hilbert, DuckDB spatial extension. You need to load the spatial extension to calculate this index. And as part of the project I'm working on, there will be a Python script preparing, like you give it a normal OD data set with just like a simple plain origin destination count table. And it will prepare this kind of Parquet file sorted and with the index. Yeah, the only so this is like kind of a SQL query. You need to prepare this, but the trick is that you need to do this calculation of the Hilbert index twice, because we have let lon, right? But we have it for the origin and destination. For OD data, you don't. It's not just one point, right? It's start and end. So you can do it twice. You get it first for each for the origin and destination, let lon, and then you get 2 numbers, right? But you can also use st-hilbert for these 2 numbers you get for the origin and destination, and compress it again. So you get from 4 dimensions into single dimension. And then you sort your table by the single column flow h in this case, and then the flows which will have the same or close number in this column will be also close to each other on the map. And then we don't need to read as many chunks to represent this data. So yeah, that's it. If you want to follow this work, yeah, best is probably sqlrooms, where new stuff will be appearing. And yeah, otherwise Flowmap.gl, Flowmap.blue, Flowmap.blue-R, Flowmap.ct. And here's the example you can try. Thank you. Is there time for questions? No? Okay, sorry about that. But reach out to me.